Bonjour mes amis et bienvenue à la deuxième classe de notre deuxième unité. For those of you that don't speak French, that means I can smell you through the screen and you might want to consider a shower. Just kidding. Or am I? Either way, we're here to do some math, and specifically to continue our discussion of graphing the linear inequalities that we discussed last time. So the title of our lesson today, Class 2, Unit 2, let's talk about graphing some linear inequalities. In class together, we saw that we could test whether a number solved an inequality using substitution. Eventually, we're going to want to start thinking about how we can go about identifying solutions using inverse operations. And we're going to see that it's actually really similar to the way that we worked with equations back in Unit 1. But before we can do that, there's a little bit more to inequalities we've got to mention, specifically their visual component. So remember, the thing that's a little bit different about inequalities from equations, rather than one solution, remember, shout it out, they have how many? Oh, my eardrums. They've got infinitely many by default. So instead of a single solution, we think about a solution set. The set, shockingly, of all of our possible solutions. To visualize the solution set, remember that we drew upon an old friend from journeys past in our mathematical exploration, and its name, of course, is Jeremy. No, it's the number line. So to visualize the solution set, as we said together in class, well, an option for me is to think about quote-unquote graphing, and I just include the graphing in quotes, because the graph of a number line we don't really think of as a graph in the way that like we might think of a line or a circle, but it's still a graph. It's a visual, it's a picture. So say that I want to graph something like x is greater than -3. Look, I'll even be really nice to you. I'll give you your Jeremy. Imagine that. So I'll give you your Jeremys. Let's say that I want to think about plotting these inequalities on a number line. I don't know, take a risk, take a chance, who cares? If you had to think about the things that you'd include on this number line to make your graph complete, what do you think would be there? Play around, see what you come up with, and then we'll chat. Alrighty, my friends, playtime's over. X is greater than -3. So a lot of this is going to be me talking you through some conventions that you'll see. And again, as we established in class, right, a convention, it's just like a mathematical best practice or habit that we agreed upon to try our best to avoid some miscommunications. X is greater than -3. Well, first thing I probably want to do is label my number line. So on my number line, I'm going to give myself some tick marks. It doesn't really matter where the -3 goes. Often we think about putting it kind of towards the middle because it's the thing that's important to the inequality, but it could be anywhere. I'm not a big stickler for labeling the entire number line, but I do think it's important to give a little bit of scale. So off to either side of the -3, I'll include one or two things, maybe I'll count by ones here, just to indicate what the distance between each of my tick marks is. And then I often like to include my little 3 dots, called an ellipsis, by the way, if you didn't already know, to indicate that I'm going beyond those values. Okay. Another label that you'll often see me do, that not every mathematician does, but I like to. When I'm working with a number line, I often will label my number line with the variable that's associated with it. So here I remember that I'm talking specifically about values of x. Now, I want values of x specifically that are greater than -3. With that in mind, 5 seconds, what part of the number line do I care about? Bigger than -3? Am I to the right or to the left? Go. 4, 3, 2, 1. Okay. Well, if I'm greater, then I probably want things that are out in space. No, I want things that are to the right on the number line. So in some way, I'm going to shade in the parts of my number line to the right of this -3. I'm using like a solid line here, but you could use a squiggle, you could use a scribble, whatever you want to do. The other thing that you'll see that I've done here, my number line continues past the point of my paper where I've stopped the line itself. So to indicate that I keep going, I've drawn in this arrowhead, right? I'm interested in all values greater than -3, not just the ones that I can see on the number line that I've drawn. Now the -3 poses a bit of a problem because it's not actually included in the solution set, right? I need to be bigger than the -3, so I can't shade in the -3. The way that I'm going to solve that problem, because the -3 is important, I still want to label it in some way. The label I'm going to use for it here, or the symbol around it, I'm going to draw a circle around my -3. It's important enough that the inequality hinges on it, but not so important that it gets shaded in. So it's kind of like a test bubble, right? It's not an answer to my question. I can't shade in that test bubble. Using what you've learned here about graphing x is greater than -3, try to build your graph of y is less than or equal to 1/4. Give yourself a minute, pause the video, play around. Let's do it. And stop. So my first move, let's label my number line. So I'll give myself a couple tick marks. I'll put my 1/4 in somewhere. It doesn't really matter where it is. And then maybe I'll count by fourths. So 1/4 to the right of 1/4 would be 2/4, but 2/4 is of course really 1/2, followed by 3/4, and then I could keep going. 1/4 less than 1/4 is 0/4, which is really 0, followed by -1/4, and then I could keep going to the left. I'll label this with a y. Again, you don't strictly have to, but I like to get into the habit of indicating what my variable is. And then the y here, I want things that are less than or equal to the 1/4. So the part of the number line that I'm interested in is to the left of my 1/4. I'll indicate here that I want values all the way smaller than 1/4, so I'll shade in that arrowhead as well. I can keep going. And then my 1/4 here. It's the thing that my inequality revolves around, so it's still going to get circled. But is 1/4 in the solution set or not? 5 seconds, what do you think? Okay, well, because it's less than or equal to, yes, I could be equal to the 1/4. 1/4 is in my solution set. So again, just like you would shade in a right answer on a test, I'm going to shade in my bubble around the 1/4. It is an answer to my question. It is included in my solution set. Congratulations, you've graphed your inequalities. Attached to the graphs of your inequalities, by the way, 2 forms of notation that you might see, especially once you get into upper level math. The first one is called set builder notation, and the second is called interval notation. I'm not expecting that you've seen either of these before, so I'm going to talk to you a little bit about how these work. The idea behind set builder notation is that I want to indicate what criteria I need to meet to be included in the solution set. When I'm talking about sets, mathematically, sets are often referred to using these kind of squiggly brackets. They're really called braces, of course, but I like to say squiggly bracket because it sounds more fun and I like to have fun. So, the way that set builder notation is written is as follows. I've got my squiggly bracket, and inside of my squiggly bracket, I'm interested in values of x, and then next to this x, you'll see a vertical line or a bar. He's got bars. So, this bar, it actually means something. It's a piece of mathematical language. The way that this translates, it means such that. So what I'm saying here is that in my set, I'm interested in values of x such that, in other words, meeting the particular criteria. Well, what's the thing that needs to be true about x to be in the solution set? Well, it needs to be greater than -3. So here's my set builder notation. All values of x such that x is greater than -3. My set builder notation for y here, let's write it together. Well, I'm interested in the set indicated by my squiggle of all values of y such that, meeting the criteria, well, what criteria needs to be true here to be in the solution set? Well, y just needs to be less than or equal to 1/4, and then I'll close my set using my end squiggly bracket. By the way, notice here, what do you see might be a cheat code for writing your set builder notation? 5, 4, 3, 2, 1. Well, maybe you clocked it, maybe you didn't. Notice that the thing in the second half of the set builder notation is just whatever your inequality statement is. So once you've gotten to that place, all you need to do is slot it into your set builder notation, and you're able to build that notation out. Interval notation, however, is slightly different. Where set builder notation tells me the criteria I need to meet, interval notation tells me what interval or what part of the number line do I care about? So for x is greater than negative 3, I care about the part of the number line that I've shaded in. So I want everything bigger than negative 3. To write interval notation, I move from left to right. Well, on the left, the starting point of the shaded in region of my graph here, it begins with the negative 3. It's not included, but it determines where I start. And then where do I end? Well, in this case, I actually don't end. I keep going so I can get infinitely big. So my interval notation is from negative 3 to infinity and beyond. In this case here, the only thing that's going to change about my interval notation is whether or not a value is in or out of the solution set. We said negative 3 here is not in the solution set. In interval notation, to indicate that something is not included, it gets a parentheses. And for infinity, you might be wondering, well, is it included or not? Well, the thing about infinity that's a little bit wonky, infinity, you might remember, is not actually a number. It's a concept. It's an idea. So because it's not a number, it can't actually be in the solution set. I can't plug in infinity. So because it's an idea, it will never be included. It will always get a parentheses, a bit of a cheat code for you. So for the one on the right here, the interval notation is going to change in two ways. First of all, notice that my arrowhead is flipped. I want everything less than 1/4. So now, if I'm reading from left to right, well, now I'm not going to start at 1/4, but end at 1/4. And then to the left here, by the way, I forgot to mention, there's a comma that you include in between the start and end points. Well, the starting point of my graph is something really, really small. In fact, infinitely small. The way that we'll indicate that is negative infinity. So I'm going off in the negative direction, off towards something really, really small. Negative infinity, just like positive infinity, it's an idea, it's a concept, it's not a number, so it can't be included, it gets a parentheses. But 1/4 is in the solution set. In interval notation, to indicate that a value is included in the solution set, rather than a parentheses, mathematicians decided on a square bracket to indicate inclusion in the solution set. Cool. So with that in mind, let's jot that down. If a value is not in the solution set, what do you notice it gets in the graph? What do you notice it gets in the notation? If it is in the solution set, what do you notice it gets in the graph, gets in the notation? Take 20 seconds, look at those graphs above you, look at those notations above you. What do you notice they have in common? Go! And stop. If it's not in the solution set, notice on the graph, for our values of x here, they'll always have an open circle. So our circle will not be filled in. If it's in the solution set, though, I fill in my circle, so I think of this as a closed circle. I was going to write circle closed, which, is true. I guess if you were thinking like Frenchly, then it would be a circle closed. But I get a closed circle. For my interval notation, notice the set builder notation looks the same either way. You just slot your thing in. But for a value that's not in the solution set, interval notation gives it a parentheses, whereas if it's in the solution set, it gives it a bracket. Very nice. So with that in mind, right now your notations might feel a little bit weird. The only way they're going to feel less weird and less scary is if we do some practice. So I'm going to scroll down. Taking what you've learned here, let's build out the graphs of the following 3 inequalities and state their notations. So, plot your graphs, label your number lines, and then give me your set builder and your interval notation. Set a 3-minute timer, see how far you get, and then we'll come back together. Go, go, go. And stop. Q is greater than -2. So taking what we've learned here, I want to label my number line, draw my graph, and write my notations. So Q is greater than -2. Maybe I'll plot my -2 in the middle. Of course, it doesn't have to be. and then I'll count maybe by ones. So I'll say -1, -3. I'll give myself my ellipsis on either side to indicate that I keep going past these numbers. -2, is it in or out of the solution set? Well, it's out of the solution set. So the -2 is important, but not important enough to be included. And then I want values of q here that are bigger than the -2. So I'm going to shade in the part of my number line to the right of -2, shade in my arrowhead to indicate that I keep going. And then my last piece of notation, I'll label my graph with my q. Fantastic, let's do our notations. For our set builder notation, I often abbreviate it as SB for set builder. Well, I'm interested in the set, indicated by my squiggle, of all values of q, such that my vertical bar, well, the criteria that I need to meet here is that q needs to be greater than -2. So again, my cheat code, I just slot my inequality right into my set builder. And then for my interval notation, again, here I'm talking about the part of the number line that I care about. Well, the part of the number line that I'm shading in starts at -2, and then it keeps going, keeps going, keeps going, and never stops. So it goes to infinity. Infinity, of course, is never included. Again, it's a concept, so it always gets a parentheses. -2, we said, is out of our solution set, so it also gets a parentheses. Cool. Let's do the next two. I'll go a little quicker. 5/2 is greater than or equal to z. So don't get tripped up here because the z is on the other side. I'm still going to label everything as I would. So I'm going to slot my 5/2. Maybe I'll count by halves. So my next half would be 6/2, but that's really 3. To the left would be 4/2, but that's really 2. And then I could keep going. I'll label with my variable z. I want values of z that are, in this case, the z needs to be smaller. Notice where your alligator mouth is pointing. So I need to be to the left of the 5/2. Shade in my arrowhead as well. And then I want to be around 5/2. It could be equal to 5/2. So it's going to give me a closed circle. My set builder notation, well, I'm interested in the set of all values of z such that z, in this case, you could say is less than or equal to. I'll just rewrite it as 5/2 is greater than or equal to z. And then for interval notation, looking at my graph, well, I'm starting to the left at -infinity. -infinity is never included. It always gets a parentheses. And I go and stop at 5/2. 5/2 is in the solution set, so it gets a square bracket. And finally, n is less than 0. So on my number line, I'm going to label maybe zeros here. I'll count by ones, so 1 and -1. Keep going off to either side. In this case, my variable is n, so I'll label my graph. N is not included in the solution set. It's either less than or greater than. That always gives me an open circle. And then I want values of n that are less than 0, so I want to be to the left on my number line. Shade in your arrowhead, and we're Gucci. For our set builder notation, well, I want all values of n such that n is less than 0. And for my interval notation, well, I'm interested in the part of the number line that starts at -infinity, something infinitely small, and stops at 0. -infinity is never included, so it always gets a parentheses. And 0 here has an open circle. It's not included. It also gets a parentheses. Fantastic. So now I know how to build a graph given an inequality statement. What if I put that down, flip it, and reverse it? What if I want to reverse engineer the inequality statement from the picture? So take 30 seconds, pause the video. Let's write the inequality that corresponds to each of these graphs. Go ahead. And stop. So for our first one, our variable here is h. I can read my label. And what do I know about h? Well, it has a closed circle around 48, and then it's everything off to the left. So if I'm to the left of 48, I need to be less than, because I have a closed circle that tells me 48 is a possible solution, so less than or equal to is going to need to be my sign. And for this one here, well, I've got u as my variable. I've got an open circle around this one that's unlabeled. Well, how can I figure out what that label is? Notice it's between negative 28 and negative 27. And knowing that my scale is consistent, well, halfway between here would have to be 27.5. So this is like negative 27.25 or 27 and a quarter. So u here in this case, open circle, it's not included, and arrow pointing off to the right, so it needs to be strictly greater than that negative 27.25.